Now let's apply our theorem to the next situation where we're going to take a fourfold axis and combine it with a mirror plane. And what I'm showing you here on the title slide is what the answer is going to be, which is we're going to arrive at a 2 mm, much like we had derived a 3 mm. So this time we're going to do a square with a mirror plane. Now one interesting thing is one problem is that you're going to create an automatic other mirror plane that's not unique because of the fourfold symmetry. So what I mean by that is that if I put sigma 1 through here by that addition, right, because I have a rotation of 90 degrees in fourfold symmetry, I'm automatically going to produce a non-unique mirror plane called sigma 2. Sigma 2 and sigma 1 are the same because the fourfold symmetry automatically causes that. It is not created by our combination theorem, right? So I'm going to have sigma 2 anyway, which is 90 degrees rotated from sigma 1 just by the fourfold symmetry. So let's forget about that for a second and hold on, sorry. And let's look at any new induced mirror planes that are created by our theorem. Now, if I combine sigma 1 plus that and it just gives me the 90-degree one, it actually means that I would have no unique mirror planes. And so it would be called 4M because the other one isn't unique. So in other words, because of the fourfold symmetry, if all I get from combining sigma 1 plus the fourfold axis is another mirror plane going through here that was going to be induced anyway from the fourfold axis, right, rotation of pi over 2. That's not a new element, right? Just like we showed before in the group, this fourfold symmetry is already going to have rotations of everything by pi over 2, right? So it means that if all I get from the combination of this is a mirror plane rotated pi over 2, it actually is not unique, and I would just be calling it 4M. So let's look at using our theorem to say, all right, what are some unique combination? Will sigma 2 be 90 degrees, or is it another rotation that identifies a unique plane? And so, in fact, I think you know the answer, which is since this is half of the rotation angle, that we're going to have actually a new unique plane. So if we just go through this, remember that this means that we're doing rotations of pi over 2. That's the this is a pi over 2. So it means that our element here is pi over 2. So that means that mu equals pi over 4, which is 45 degrees. So that means this is pi over 4. So actually, that means that the addition of these two guys, even without the fourfold symmetry, creates, here's sigma 1, and then 45 degrees away, it creates a unique plane, sigma 2. That's 45 degrees, pi over 4, 45 degrees. And so if I then take and say, well, I know from rotation that I'm going to get a sigma 2 anyway, because remember, this is not a unique structure because in a fourfold axis, everything gets repeated and rotated over pi over 2. So sigma 1 and sigma 2, sorry, if I call this sigma 3. So sigma 3 and are same type of plane, where sigma 2 is unique and generated by this combination theorem, which means it creates another whole distinct element. So now if I were to draw all of this together, we have these mirror planes. And this mirror plane is different than this mirror plane. And therefore, as our notation showed before, we have the fourfold axis. We've got sigma, but then we need to have another m. So this is called the 4mm space group, and of course I'm just drawing the blue here to connect you to what I'm talking about, but of course, you don't need to use multicolors. It's called 4mm in international notation. So I hope that is pretty clear. If we were to show you a motif, by the way, I think it's very important to show you a motif because there's something kind of subtle here which I want to make sure I get across. So let's suppose I have these little black objects that are reflected about sigma. That gets rotated, of course, so they have to be over here. So again, you can see how the red are reproducing, just the red symmetry itself is producing these objects at each place. If I got this correct, I always have to watch myself which way I put the tails. So you can see here, fourfold symmetry, they get rotated, they reflect about the red, so that is sort of a 4m. But now you can see why our theorem kind of orients us into understanding that we have the blue, because you can clearly see here something that is already in the symmetry that we could have done by inspection, but we don't need to now that we have our theorem, is that these objects, for example, are reflected about the blue plane, and this object is reflected about the blue plane, and this object is too, and so on. So we actually get the blue sigmas automatically once you put the motif in, and that's another way to think about it. So again, what we're actually doing is this theorem is telling us that if we have two group members, like a fourfold axis and a sigma, I already know I'm going to get all the red. And if I put a motif in, it's going to reproduce all these, right? But I get new elements automatically induced mathematically into the group because this theorem always has to be true geometrically. So it tells me that I have this other mirror axis in here. Now if I were doing it through inspection, the way I would see this is I would, with red, draw these objects like I said, and then I'd recognize, hey, you know what? Everything here is being reflected across here. There must be a mirror plane here and here. And the way you could see that those are unique mirror planes is that these two objects are near the red, for example, the way I've drawn it on purpose here. And these objects are reflecting about the red. But notice how I don't see any two objects sitting here close that are reflected around the blue. It's a different mirror plane. The localization of things around the blue is different from the red. And that's another way, pictorially, graphically, to see that the blue sigma is different from the red sigma. It's there, and I could have seen it by inspection, but with my theorem, I know that as long as I'm doing the red, I'm automatically going to have, the blue induced. And so that's a good idea on that's a good way to see how, again, we're doing these graphical things, which, I keep on saying is like inspection, but they're related to the math behind group theory, because again, blue is another element of the group by definition, because if I have a rotation and I have a sigma, it automatically can induce that one. Or vice versa, if I had done it where I created two mirror planes and then threw in a fourfold axis, would tell me, the uniqueness between sigma 1 and sigma 2 based on this theorem. Okay? So one last point is some language, again related to group theory, about the rank. So this is for MM would be called a rank 8. So it's a group of rank 8 because you have 4 rotations and 4 reflections. So again, if I were looking at the group theory, right, and I were to write it out in the brackets, right, I would have, I've got 1, 2, 3, 4 planes. Sorry, 4 rotation objects and 4 reflections, and that creates 8 objects. So I have 8M. So in other words, the other way to think about it is if I look at the point group and I look at the motifs, the rank equals the number of the motifs that I have there. So if I count these up, I've got 1, 2, 3, 4, 5, 6, 7, 8. Right? So if I put one object here and I look at the symmetries and what it forces me to create, the number of objects created by all the symmetry elements on that initial one, the way I've drawn it here, one black comma-like object, I would produce all these guys everywhere. And that's another way you can see that you have rank. But this rank is composed of 4 rotations and 4 reflections. Again, the number is always related to the original symmetry, right? So we saw that with a twofold axis had 2 elements in the group, and a threefold rotational element had 3, right? So you know right away that the 4 is going to produce 4 right away, and then you get 2 mirror planes for each one of the distinct ones. So there's 4, so 2 of the reflections are red, 2 are blue, and then the rotations are just the 4 angles from the rotational axis. Okay?